So hello everyone. So we're going to consider, again, a very simple problem, but one that is pretty deep in the physics. There's lots of interesting physics going on when you dig a little bit deeper beneath the surface. Okay, and this problem is great for two reasons. One, it focuses on and really helps to reinforce the idea of Newton's third law, which you all know from high school physics. It's a action and reaction pairs of forces. And this will really remind you of that super important concept. We're going to be drawing free body diagrams where there's three objects in motion, and we have to identify and make sure there are proper action and reaction pairs between the various diagrams. Okay, that's one thing. But also, it focuses on, or it involves relative acceleration, which is really interesting, as you'll see. At the end, we're going to grind through some math or whatever. We'll get some answer, and then we'll look at that answer, we'll scratch our heads, and then we'll say, you know what? I can understand that answer in a beautiful and elegant way if I consider an observer who is moving in an accelerated frame of reference. And you know what they see, what they experience is artificial gravity. And so it's a really nice way to interpret the answer of this question. So it involves some fun physics like artificial gravity. So enough of that. What is the problem? So what we have is three blocks. Okay, so the first is a large block, which has mass big M, and mass big M is sitting on a flat horizontal surface. Okay, and then sitting on top of big M is a block of mass M2. Okay, and attached to the right-hand side of the block of mass M2 is a rope or a string. And that rope or a string is passed over a frictionless, massless ideal pulley. Okay, so there's no friction here, there's no effort to get that pulley spinning or whatever. And that pulley is rigidly attached to the top right corner of big M. Okay, so then we take that rope and we pass it over the pulley, and we attach it to a second block of mass M1. Okay, great. So that's our setup. And what I want to say is that this problem will already be interesting enough without the introduction of friction. So just to keep things as simple as possible, all surfaces of contact between blocks are frictionless, and blocks and ground. So no friction anywhere in sight. Okay, so big M is free to slide frictionlessly on the ground, M2 is free to slide frictionlessly on top of big M, and M1, if it's pushed against big M, is free to slide up and down frictionlessly. Okay, just to keep things simple. So now we wonder, well, what could possibly be interesting about this problem? Well, first of all, let's look at the basics. Okay, so let's simplify it even further than it is now, and let's take big M and let's clamp it to the ground. So it's like a table fixed in position. And so all we have is a block of mass M2 that can slide on a frictionless tabletop, and M1 can fall down. So now we take M1 and M2 and we hold them fixed in position initially, and then we let go. What's going to happen? Well, obviously M1 is going to accelerate down, and M2 is going to accelerate to the right. The acceleration of M1 down is going to equal the acceleration of M2 to the right. The velocity of M1 down at any instant of time will equal the velocity of M2 to the right at any instant of time. Okay, so that's obvious. And that problem is trivially solved. Okay, you know, what's the acceleration of this system, right? That's trivial. So so we are going to make it more interesting by allowing M to slide here. But before we do so, I just want to keep on with this very, very simple example. First of all, when you release the two masses and let them go and do what they want to do, then this rope will be under tension, an amount of tension T. Let me just remind you about the basics of a rope being under tension. So I imagine I have a piece of rope here. What I've done is I've grabbed both ends and I pull like this. Okay, so if I exert a force to the right with 10 newtons, then I have to exert a force on the left end to the left of 10 newtons as well. Obviously, the forces can't be unbalanced. If this is 15 newtons and that's 10 newtons, well, then that chunk of rope's going to accelerate, right? So if it's not accelerating, well, the forces are obviously equal. Now, I want you to remember, and this is important, you know, when we talk about normal forces and so on, and forces of static friction, they all have the same origin. You can think of them as simply due to imagining that all matter is just made up of little point particles, some little point masses, all attached by little tiny springs. Okay, in reality, it's little charged particles interacting through electrostatic forces, but for the purposes of this course, it's just perfectly good model to just say, oh yeah, everything's just little springs. So that when you push against the wall like this, what you're doing is all those little springs in the wall are being compressed a little, and they're pushing back with exactly the same force that I've compressed them with, okay? That's the origin of the normal force, the force of static friction, all that stuff. It's the same thing with this rope, okay? So now I take this rope, which I'm thinking of as a little spring. Maybe it's a very stiff spring, right? You got to pull hard on a rope in order to get it to stretch a bit. So it's like a very stiff spring, but nevertheless, it's a spring, okay? And so you pull like this, and so you've put it under tension, okay? And if you say that it's under a tension of, suppose I'm applying a force of 10 newtons at both ends. Great. We say that the tension in this string or rope is 10 newtons, which means that if I were to now take a block and attach it to the right end of that string and keep a force of 10 newtons to the left on this end and let go, what will happen is everything will accelerate to the left like this. I'm applying a force of 10 newtons to the left, onto the left end of that string, and that string will maintain a tension of 10 newtons, and so then that the right end of that spring or string will apply a force on the block of 10 newtons, and then the whole thing will accelerate together. Now, another just minor point here, but important one, is that that any length of string in Physics 121 is considered to be massless, okay? Because of course you realize that if that chunk of string had mass, then if it's going to be accelerating, it needs to have unbalanced forces. 10 newtons at this end, maybe 9 newtons at this end. So a net force of 1 newton causing that massive chunk of string or spring or rope or whatever to accelerate along with the block. We're just assuming that these chunks of string are massless, and so they require 0 unbalanced forces to cause them to accelerate any amount you want. Okay, so anyways, so the idea is if that chunk of rope is under a tension T, it means that that rope is exerting a force on M1 of magnitude F in the upward direction, in addition to any other forces like gravity and so on that might be acting. Okay, and then the other thing to say is if this is a massless, frictionless pulley, then if that part of the string is under tension T, that part's under tension T as well. That's easy to see. Okay, so if I take a piece of string, slack piece of string, and I lay it across there, if I pull down with 10 newtons here, I got to pull with 10 newtons here. Okay, so if this guy is exerting an upward force of magnitude T on M1, then this end of the rope is exerting a rightward force of magnitude T on M2. Okay, so that's important. I also want to say that we don't know what the tension is. Okay? The tension is not equal to the weight of M1. It can't be, right? So if big M is pinned to the ground, can't move like a fixed table, and we release this system, M1 is obviously accelerating down. Well, if it's accelerating down, going faster and faster and faster down, there must be an unbalanced force in the downward direction. Well, what are the forces acting? Well, there's the weight pulling it down. The tension can't equal the weight. If the tension equaled the weight, well, then there'd be no net force, and M1 could only move with constant speed up or down, okay, or 0. Okay? Its velocity can't be changing. So if M1 is accelerating down, then the tension in that rope must be less than the weight, so that there is a net downward force causing M1 to accelerate downwards. Okay, so we don't know what the tension is, and that's one of the things we're going to be solving for. Okay? Great. I should say that this entire thing is happening in a gravitational field G. Okay, what else? Okay, so now what we're going to do is we're going to say, let's take this big block M and unpin it from the ground and let it slide freely. And now we're going to ask the same question. If I take now all 3 masses and hold them initially at rest and then release, what's going to happen? Well, basically the same thing. M1 is going to accelerate down, M2 is going to accelerate to the right, but what about big M? Well, obviously big M isn't going to accelerate up or down. If there's any acceleration, it's going to be to the right or to the left. Okay, so then what could cause an acceleration to the right or to the left? Well, are there any forces acting to the right or to the left on big M? Oh, look, we have a tension. Okay, so that tension T, this rope is under, physically you know that this rope is under tension. That tension is the only force pulling to the, horizontally, it's pulling to the right on M2, causing it to accelerate to the right. Okay, but that tension is also touching that pulley and pulling to the left. Think about it this way. Imagine going back to my rope, my slack rope, which I lay over top of that pulley, and I pull down 10 newtons here, 10 newtons here, gunk. It's obvious that that rope is going to be exerting a force that way, at 45 degrees, into the top corner of that mass. And that force at 45 degrees pushing on big M, the big M block, has a component in the horizontal direction of magnitude T to the left, and in the downward direction of magnitude T. Okay? So that rope is exerting a force that way and that way on big M. The force that way exerted on big M pushes big M into the ground harder, and so the normal force that the compressed atoms of the ground exert back up is going to be larger. So tension T will affect the normal force, but the tension T here is pulling this way on the top right corner of that mass, and it's going to cause that mass big M to accelerate to the left. Remember, M2, there's no friction between M2 and M, so M2 cannot exert any sideways forces. No matter what it's doing back and forth, it cannot exert any sideways forces on big M. It can only exert a downward force. Surfaces that are frictionless, the only direction of force between them is perpendicular. There can be no tangential friction forces because there's no friction. Okay? Right. So, great. So, if we hold all three masses at rest initially and let go, we're going to have the obvious thing happen, but then there's something new and interesting that happens, which means big M, which is that big M accelerates to the left. Okay? So then you start thinking about it and you say, well, what if I applied a force on the left side? Now with my hand, I'm going to be pushing. Okay? So I can certainly push hard enough to keep this mass, big M, from accelerating to the left when I release everything. Okay, so I'll imagine that case first. I'm applying a gentle force to the right here, release everything, and I adjust the force. I make the force exactly such that big M doesn't move. Okay, because certainly if it were pinned to the table, it's precisely those pins that are in the ground are exerting that force on big M, keeping it from accelerating to the left. So I can clearly do that. Okay. So then, what else could be interesting about this? I mean, so what? Here's something. Let's imagine taking that force and not making it small, but making it much larger. Okay, so this is going to be my applied force. Okay, what if I make it super large? Okay, I push just like crazy. I just like brute force do this so that no matter what's happening with M1 and M2, big M is definitely accelerating hard to the right. That means that this point is accelerating hard to the right. Okay, it's picking up speed faster and faster and faster, faster to the right like this. And so what's that going to do? Well, it's going to put this piece of rope under a lot of tension because M2 has inertia. It started at rest, it wants to stay at rest. If it's got some inertia, you have to exert a force on it to cause it to accelerate. And for M2 to have any chance of even a little bit, staying up with big M, okay, there has to be, if the acceleration of big M is large, the acceleration of M2 will also be large. And so to cause that large acceleration means a large tension. Large tension on this section of the rope means large tension in this section of the rope. And so the tension in this section of the rope, we can make it easily. If we push hard enough, we can make this tension easily exceed the weight of M1. So now there are unbalanced vertical forces on M1 causing it to accelerate up. And so now, if you push really hard on big M, then you'll see that, yes, M1 is going to accelerate up, okay, and M2 will accelerate back, okay? But it'll accelerate back relative to big M. It's still always accelerating to the right because the only force on it is to the right. So if it's going to accelerate at all, it's going to be to the right. It's just that when M1 is accelerating up and M2 is accelerating back, that's an acceleration relative to big M. Someone sitting on big M would see, yes, M2 is accelerating back. But someone sitting on the ground in the original inertial reference frame will see both big M and M2 accelerating to the right, just that M2 will not be accelerating to the right as much as big M. Okay, relative acceleration. That's kind of cool. That's one of the interesting aspects of this problem. Okay, so, so clearly, when I apply a very gentle force, then M1 will accelerate down. When I apply a very hard force, M1 will accelerate up. So then, well, here's an interesting potential question. What precisely what force, let's say F, we'll call it F0 later, a critical value of force, do I need to apply so that M1 has neither a positive nor a negative vertical acceleration. It just stays exactly this distance off the ground. Okay? So that's the kind of question that we might be interested. In general, we will be interested in the relationship between how strong the force is, the applied force, and the vertical acceleration of M1. Okay? So, accelerations. So first of all, this is a somewhat detailed problem in terms of accelerations, acceleration vectors. Okay, and so what we're going to do is we're going to introduce axes. And so we'll put, say, I hat to the right. All of the forces in this problem are vertical or horizontal. The obvious choice of orientation for your I hat and J hat are, let's say, I hat to the right and J hat up, as opposed to the thing tilted at some angle. Okay, so very good. And then we will say that this force, just erase that. So then this force is equal to some number F in the I hat direction. Okay, so we're going like that. If F is a positive number, the force is being applied this way. If F is a negative number, the force is being applied this way. Okay, we will only consider positive numbers here. Because otherwise, if you make this guy accelerate this guy this way, then this M1 just sort of stays hanging there, and then the rope, whatever, the space increases here, and then this pulley moves over to here, and then this thing starts oscillating like a pendulum, and the problem becomes very, very complicated. We're trying to push to the right so that M1 stays pushed up against big M, okay, to keep things as simple as possible. Great, and so we know, yeah, we're applying this force, and big M is going to accelerate, obviously, to the right. Let's give it a variable, because we don't know what that acceleration is. So the acceleration of big M, we're going to call big A, and it's equal to some number big A times I hat. If big A is a positive number, M is accelerating to the right. If big A is a negative number, M is accelerating to the left. Okay, and A is a variable. We don't know what that is, so we're going to be solving for that. It's going to be one of our variables in our equation. Equations. Okay, so next we're going to say that, yeah, at the end of the day, I know that from the point of view of someone sitting at rest on big M, sitting on the big block, okay, that's going to be accelerating, and they're going to see the little block M1 accelerating up or down. If we push really hard, it accelerates up. If we don't push so hard, it accelerates down. If we push at the critical value, it doesn't accelerate. So we need to give a vertical component to this acceleration. And so we're going to call this vertical component of the acceleration, we're going to call that A relative. And relative because it is the acceleration that someone sees from the point of view of being attached to big M, which is an accelerating object. So relative to that accelerating object, we're going to give that, it's going to be in the J hat direction, so in the upwards direction. Okay, and we're going to have an unknown amplitude of that acceleration, or amount of that acceleration. If alpha is a positive number, it means M1 is accelerating up from the point of view of someone sitting on big M. If alpha is a negative number, then M1 is accelerating down from the point of view of someone sitting on big M. That's the relative acceleration. However, and now this is the super important point, such relative accelerations, accelerations seen by observers, attached to accelerated objects, in other words, observers in an accelerated reference frame, those are not the kinds of accelerations that appear in Newton's second law. Okay, so in Newton's second law, all of the accelerations are referred to accelerations relative to a given initially chosen inertial frame of reference. Inertial frame of reference, not accelerating. When you're accelerating, you introduce, so-called fictitious forces. Anyways, Einstein wouldn't call them fictitious; they're real gravitational forces. But fictitious forces or artificial gravitational forces. Okay, that's what we're actually going to come to later. Okay, so anyways, so we don't really, in terms of Newton's second law applied in an inertial reference frame, this isn't the acceleration that we're interested in. What we're interested in is what is the acceleration of mass m1 relative to the inertial reference frame? Well, from the point of view of someone sitting on m, there's, say, an acceleration up like this, but the person sitting on m is himself accelerating to the right. And so the acceleration of m1 will have a component that way, and will also have a component that way, which equals big A. Okay? And so the actual acceleration, the inertial acceleration of m1 in the original inertial reference frame is actually in this direction. Assuming that A relative is up, the actual acceleration block number 1 will have a horizontal and a vertical component. And what are those? Well, A1, the horizontal component is obviously the same as the acceleration of big M, and the vertical component will be the same as the acceleration of the upward acceleration that someone sees who's attached to big M. So that's plus A relative. Okay, and so in terms of a picture, we would draw this as A, this is A, I'm adding them vectorially, plus A relative is up like this. So adding them tip to tail, I get A plus A relative is this one. So this is the acceleration of M1 in the original inertial reference frame. Great. That's the one that goes in Newton's second law. Now, the last object we need to consider is the acceleration of M2. So M2 is going to have some acceleration as well, so A2. So what's that going to be? Well, that is going to be in the I hat direction. So it's something times I hat. So if alpha is 0 and M1 is not accelerating up or down relative to big M, then M2 is not accelerating left or right relative to big M. So if alpha is 0, then the acceleration of M2 is the same as the acceleration of big M, and so it's just equal to A. Okay? However, if alpha is positive, so M1 is accelerating up relative to big M, then M2 will be accelerating back relative to M. And so we have to subtract alpha. Okay? So that's the acceleration of M2 to the right. And remember, this is important, that even though you've got some alpha there, and it looks like, ooh, maybe that could be negative, it's never negative, because the only force that's acting on M2 is either 0, if that's under 0 tension, or positive, to the right. Okay, and so M2 will always be accelerating to the right relative to the original reference frame, even though it might be accelerating to the left relative to big M. Okay, I think that's it. Very good. And so at the end of the day, what we want to figure out is, what is f as a function of alpha? Okay, so if we want alpha, say, to be a large positive number, how hard do we have to push? If we want, say, alpha to be a small negative number, then how much more lightly do we need to push? If we want, say, alpha to equal 0, that critical value force, what is the required force? So we want a relationship between the applied force, the strength of the applied force, and the up or down acceleration. So that's what we're looking for in this problem ultimately. Okay, so how do we do this? So, well, this is definitely a dynamics problem, and we have 3 objects that are dynamical here. All 3 objects have accelerations, and so what we need to do is draw a free body diagram for each one of those objects, and we need to show all of the forces that are acting on that object, not the forces that not the forces exerted by that object on other things, but the forces exerted on the object of interest by other things. Okay, so let's work this out. So normally we draw free body diagrams as point particles. Because there are so many forces here, I'm gonna draw it as a box. Okay, so here's the free body diagram for big M. So we have a block, big M. Okay, so it has a mass, big M, and we think about the various forces that are acting. Remember, 2 categories: field forces, gravity, electrostatic, magnetic, whatever, and then contact forces. What's touching that object, exerting forces, string, ground, whatever, other blocks or whatever. So we say, yes, field force, there's gravity pulling down. So we definitely have an mg, a force of magnitude mg going down. Okay, and then we think, so that's it, that's the field force. What about the contact forces? Well, what's touching big M? Ground. Okay, but remember that whenever you have a frictionless surface, those frictionless surfaces exert forces on each other, but only perpendicular, because there are no sideways friction forces. Okay, and so the ground is touching the big M, and it will exert a force in that direction, just straight up. Okay, so that's N of magnitude big N going up like that. We have no idea what that normal force is, because there's also the weight of M2, there's also this tension pulling down, and so on. It's a variable in the problem. What else? Okay, so as we go around, we're pushing on it to the left with our hand, so there's obviously a force pushing to the right of some amount F. And then we've got M2 is sitting up here. Remember, this is a frictionless surface. Doesn't matter what M2 is doing back and forth relative to M. It can't exert horizontal forces on big M. It can only exert a vertical force. And so there will be a vertical force pushing down on the top, and we'll call that a normal force, little n subscript 2, referring to mass little m2. And what else? And also, we're going to be pushing this guy, we're going to be pushing hard, causing M to accelerate to the right. And so obviously this M1 is pushed right up against big M. Okay, and so big M is exerting a force on little m1, causing it to accelerate to the right, but these are all springy objects, and so so little m1 compresses a little bit, acts like a spring, and pushes back on big M. Okay, and so little m1 is going to be pushing back on big M, okay, with a normal force. Again, a force, because it's frictionless, there's only one component of force, and it's normal. We'll call that the normal force little n1. Little n1 associated with the block of mass little m1. Okay, are we done? No! We forgot one of the most important ones, and that's the rope. Remember, super important. I've taken a rope and I've put it over and I've pulled like this. Okay, that rope is exerting a force like that on big M. One component is T in that direction, the other component is T in that direction. Okay, so we must include this. What's touching big M? Well, the rope is touching. So the rope is exerting a force, and what is it? Well, we'll put it up here. There's a force of magnitude T going down. There's a force of magnitude T going to the left. So that's a pretty complicated set of forces acting on big M. Fortunately, they're all either to the in the I hat or J hat, so it's pretty simple. The equations are all really simple. Okay, so this is a dynamical object. The idea is whatever all these forces are, they better add up to a force in that direction, causing that acceleration big A. Okay, so all those forces add up to cause the acceleration big A. Okay. Next, we look at, say, I don't know, let's look at M1. Okay, so M1 is give me a little bit of room here. Here is M1. Great, M1. And so you think forces, field forces, contact forces. Only a gravitational field here. It pulls down with a magnitude m1g. And then we think contact forces. What's touching m1 and exerting forces on m1? Well, obviously the tension T. This rope is under tension. At that point, it pulls up with a force T of magnitude T. However, this mass, m1, is pressed tightly against mass big M. When the whole thing's accelerating like this, like I said, in order for m1 to accelerate to the right, there has to be a force to the right. and so, yeah, so basically, big M is pushing on little m1 with a unknown force, which is also of magnitude n1. So remember, this is an action-reaction pair, and I'm going to sort of emphasize that a little bit later when we're done all the diagrams. Okay, so that's that. And at the end of the day, I don't care what these forces are, they better all add up like vectors to a net force in the direction of the acceleration of m1 relative to the original inertial reference frame, which we figured out to be that one. Okay, so they better add up to an acceleration in that direction, A1, which has two components, alpha vertical and this A horizontal. Okay, and then we go on to the third object, which is mass M2. Okay, so mass M2, what are the forces acting on that mass? Well, I don't know, field force, gravity. So there's an M2G pulling down. And what are the contact forces? What objects are touching that object and hence exerting forces? Well, M2 has weight. It's pushing down on big M. It's compressing the little atoms of big M, and so those little atoms are like compressed springs pushing back up. So big M is exerting an upward force on a little m2. So I want to put that, let's put it over here, an upward force. And that'll be a force N2, which is actually the action-reaction pair for that force. Okay, and finally, at the end of the day, So we have that, and then we have another contact force is the tension. This rope is under tension. The rope is touching it. It's exerting a force that way. And in fact, remember, if you look at this, the only force acting on M2 to the right that could cause any acceleration to the right is the rope's tension T. And so at the end of the day, all those forces need to add up. In particular, T needs to be such that the acceleration of this guy is A2 to the right. And A2 is to the right, and its size is A minus alpha. Okay, so that's that. I just want to comment here, and this is super important here. This is the Newton action-reaction idea here. So whenever you have any two surfaces in contact with each other, so let's suppose we've got some surface like this, and we've got, we're touching with our finger like this, and we're like pushing into that surface there, and it's not sliding, there's some static friction here, so we're pushing into that surface. Well, remember that all of these, this piece of matter here is made up of little masses connected by little springs, and so those little springs, they get compressed in this direction. So we have a spring that gets compressed in that direction. So if we have a spring that's compressed in that direction, well, it's going to exert a force in that direction back on the thing, maybe my finger here, that was touching it. Okay, and so that's going to exert a force back on my finger of exactly equal and opposite magnitude. Remember, if I take two springs, one of them maybe they're equal springs, equal stiffness, equal spring constant. Maybe they're not. Maybe this is a stiff spring, this is a soft spring. If I push like this, if I bring those two springs together and push on the ends, then this is a soft spring. Maybe it compresses quite a bit. This is a stiff spring. It compresses only a little bit, but they will compress. Relative to their stiffness, they're going to compress in such a way that if there's 10 newtons here and 10 newtons here, then both of these springs are under a compression of 10 newtons. And so, yeah, anyways. Okay, so great. So, so whenever you push on something, it pushes back with exactly the same force and exactly equal and opposite direction. So, so let's identify. So this is a super important, basic fact about the world, but it's also a good way to check whether you've drawn all your free body diagrams to include all of the forces. So whenever you have two or more objects that are interacting with each other and touching each other and exerting forces on each other, every time you have one force acting on another object, you call that the action force. There must be a force of equal magnitude and opposite direction acting back. You could call that the reaction force. Which one you call it? You could call this one the action, this one the reaction. It doesn't matter. It's irrelevant. Okay, but there's a pair of forces of equal magnitude, opposite direction. So let's look at them. I don't know. So on here, this guy is touching this guy. And so this guy is exerting a force downwards on big M. M2 is exerting a force downwards on big M of magnitude N2. Well, then big M is exerting a force of magnitude, same magnitude, N2 upwards in the opposite direction on M2. So this, so this and this are action-reaction pairs. I'll just sort of connect them like that. What else? The tension. So actually, let's go with the normal forces first. So M1 is pushing to the left on big M with a force of magnitude N1. Well, then big M must be exerting a force to the right on little m1 of exactly the same magnitude but opposite direction. So that's an action-reaction pair. What else? We have tensions here. So this rope is exerting a force to the right on M2. Where's M2? M2 of magnitude T. Well, then that rope is exerting a force of magnitude T on backwards to the left on big M, and that's that one. So this and this are action-reaction pairs. And then finally, the rope T is exerting an upward force on M1. There it is. Okay. Well, then the rope T will exert a downward force on big M, and there that is. So that's an action-reaction pair. Okay, so if you're missing any of the pairs, if you can't like fill out those pairs, then you've missed the force. And so it's a really, really good way to check. Okay, and in fact, it's even true for one body, right? If we just had this body, there's also this force. Okay, well, I'm pushing like that on big M. Well, big M is pushing back on me, but I don't care about the effect it has on me. Okay, I'm not interested in my dynamics. I'm interested only in the dynamics of big M. So I'm thinking of this force as sort of, externally applied, and I don't really care about the back reaction on the person applying the force. Okay, but this really also has an action-reaction pair on the person applying the force. What about this one? Well, this has an action-reaction pair back on the Earth. If I take an object like this, it's got a weight of 5 newtons like this, okay? Well, then there's a force of 5 newtons acting on the Earth. And when I release this thing accelerates down and the Earth accelerates up. Here's the action force making this guy accelerate. There's a reaction force on the Earth making it accelerate up. But just because the Earth is so much more massive than this object, the acceleration of the Earth is negligible compared to the acceleration of this guy. Okay, and we usually ignore it. But remember, all forces have action-reaction pairs. Okay, it's deeply connected to the conservation of momentum. Okay, so in fact, it turns out that Newton's third law, action-reaction pair, is not quite true. If you say, for example, consider simple examples in electromagnetism, okay, where you have, positive, say, 2 charged particles moving like this. They exert magnetic forces on each other, and those magnetic forces turn out to not be action-reaction equal and opposite. So actually, Newton's third law is more deeply rooted in conservation of momentum, which is always true. Okay. And then, but certainly for all of the problems that we do in mechanics here in 121 that don't involve, say, the electromagnetic field and so on, Newton's third law is true. Very good. So we got that. What else did we want to say? I think that's about it. Great. So now what we need to do is we've written our free body diagrams down. Now we just need to apply Newton's second law. The net force, the sum of all the forces, produces these various, or causes these various accelerations. So let's do that. Okay, so there's going to be 6 equations, because we have I hat and j hat for this one, I hat and j hat for this one, I hat and j hat for this one. Let's see how much room we have. So I wonder if I should do those equations up here, and then write the final equations down here, because they're. So we'll look at. Okay, so that's our basic setup. Now we've already understood a great deal about the problem just in setting it up. Okay, now we're going to just do some math. Okay, so now we're going to say regarding mass big M, there's an I hat and a j hat component of net force equals mass times acceleration dynamical equation. Okay, so in the I hat direction, that's this way, what are the forces? Well, we have a positive F, okay, that's to the right. I want to get the order of these right. And then a minus N1, minus the magnitude of N1. What else is horizontal? And then minus in the negative direction, T. So minus T. Okay, and so all of those forces in the horizontal direction better add up to produce big M times the horizontal acceleration. So that's big M, the inertia of the big M block, times its acceleration to the right. Well, its acceleration to the right is our variable capital A. Okay, so we got that. Then in the j hat direction, which is vertical up, what are all the forces in the vertical up direction? Well, there's a normal force, positive. Okay. There is a negative, there's a downward N2 coming from M2, so it's minus N2. And then there's a tension pushing downwards. Okay. There's a minus tension from this rope here, pulling M2 down into the ground. The normal force has to be bigger. Okay, so there's that. And then finally there's the weight, the gravitational force. Okay, and so all of those forces in the vertical direction better equal the mass big M times the vertical acceleration. Well, there's no vertical acceleration, so that's equal to 0. Okay, and so from this one, I wonder if I should do this right here. Yeah, let's do this right here. So this equation here is well, okay, now let's put it over here. So this equation is trivially solved, so you just go, oh, actually, let me do that for a second. Okay, now let's go to mass M1. Okay, there's an I hat and there's a j hat component. So looking at M1, we look at in the I hat direction, what are all the forces in that direction? Well, there's only one of them. It's positive N1. So it's N1, okay, and that is equal to, it should equal the mass, the inertial mass of block M1 times the acceleration of block M1 in the x direction, in the horizontal to the right direction. Okay, so this is actually a crucial one here. Here's where we take this, or this picture here. Okay, so it's equal to M1 times the horizontal component of A1. Well, the horizontal component of the acceleration A1 is just equal to A, capital A. So that's M1 times A. Okay, so that's important. And then in the j hat direction for mass M1, we have a tension and a weight, and then the vertical component of A1. So it's T, there's a tension T in the upwards direction, there's a weight M1G pulling down, and so that's it for the vertical forces. And so that should equal the inertial mass of M1, how difficult it is to get it to change its velocity, times the acceleration A1, the y component. Okay, and so that's going to be M1 times, we're looking at what is the vertical or y component of A1. Well, that's A relative. That's the acceleration of M1 up, as seen by someone sitting on big M, which we called alpha, this variable alpha. Okay, so that's that equation. And what else? Let's look at M2. So this is M2. So what are the forces acting in the horizontal to the right direction, in the I hat direction? Well, there's only one. It's just the tension T. And so that should equal the inertial mass of object 2, how hard it is to accelerate, times its acceleration to the right. Well, its acceleration to the right is A2. Let's do it this way. This is A2x, A2 in the x direction. So that's M2. And so what is the component of the acceleration of A2 to the right? Oh, well, that's just capital A minus alpha. Okay, and then finally in the vertical upwards direction, dealing with mass M2, what have we got? We got an N2 minus a weight. So N2 minus M2G. Okay, so that better equal mass M2 times the vertical component of the acceleration. Well, M2 is only going to accelerate horizontally, and so the vertical component of the acceleration is 0. Okay, so we have 6 equations. Now, 2 of these equations are really trivial, so let's look at the very last one. So this very last one, and what this very last one tells you is that N2, the normal force, the force with which with which M2 and M are being compressed together, that force N2 is just equal to the weight. Okay? So that's pretty trivial. You could have guessed that right from the very beginning. Okay, and so then what we might want to do is take that N2 and plug it into this equation. Okay, so then this equation tells you that the normal force, we've got a bunch of stuff pulling down. The normal force that the ground has to push up with, well, what is that? Well, that's equal to negative mg taken to the right, positive mg. Negative N2 taken to the right is positive N2. Well, that's just the weight M2g, the weight of block 2. And then there's plus, the negative t goes to a plus t on this side. Okay, so these 2 equations are trivially solved, and we look at this equation and say, yeah, that makes sense, because block big M is being pushed into the ground, certainly by the weight of itself, big mg, and then add to that the weight of block M2, which is M2g, but don't forget that this block over here is attached to this string. This string, this rope, is pulling down at this point. Okay, so if M1 and M2 are not accelerating, then the tension in that string is exactly equal to the weight of M1. So M1 is pulling down, and so you have to also add the tension T, which when alpha is 0 is just M1 times G. Okay, so great. So we got that. Now what? So let's look at this equation. Let's call this equation star. Okay. If we take equation star and we substitute it into the first equation, then we can get these equations, and let me write them down here. because these are we're going to take 6 equations. We've solved 2 of them. We're going to substitute one into another. We're going to get 3 equations, sort of like the 3 main equations. We're going to reduce it from 6 equations down to 3 equations. So then this equation, we have an f, okay, and then we're going to take this equation over here for n1, and we're going to stick it into there. So we're going to have an m1a on the left-hand side, and we're going to bring a negative m1a on the left-hand side. We're going to bring that to the right-hand side. Sorry, let me just show it in this order. Let's take account of that term. Great. Then there's a negative t. Let's put that over here. Okay. And then bring everything else over to the right-hand side. So we have a big M times big A. That takes care of that term. And then we have a negative n1, which we bring to the right-hand side to write as positive n1. And positive n1 is little m1 times A. So plus little m1 times A. Okay, so that's one equation. That's important. And let's look at equation number 2. So we've dealt with this equation, this equation, this equation. We have now 2 equations left, and they're both equations for the tension T. Okay, so one of them says the tension T is equal to, I want to factor out the M1, right? Yeah, is equal to M1 times negative M1G on the left becomes positive M1G on the right. So we have positive M1 times G. And then we also have a positive M1 times alpha. Okay, so it's M1 times G plus alpha. And then we have a third equation, which is also an equation for T, which is this last one. T is equal to M2 times A minus alpha. M2 times A minus alpha. Okay, so these are the 3 key equations that we need to solve. And so, anyways, we're just a little bit of manipulation here. We're not so much interested in the normal force, you know, who really cares about how hard the ground needs to push up. Okay, and so what we really are interested in is a relationship between this variable, how hard you push, and this variable alpha, which is the acceleration up or down. And in particular, we're interested in when we set alpha equal to 0, what is the required force to make that happen, that special case happen. Okay, so what I want you to do, though, is whenever you come up with a set of simplified equations like this, you should just stare at the picture and see whether you could have gotten that without doing any work at all. Okay, so if you look at this equation, for instance, this makes perfect sense, because what you're looking at is you're saying, well, if we consider mass big M and M1, they are both accelerating with the same acceleration to the right, and that's an acceleration capital A. Okay, and so we have the mass, the inertial mass of big M, the inertial mass of little m1. That's the total inertial mass times acceleration. Well, that must be the total force acting on that system. What's the total force acting on that system? Well, there's a force F acting to the right, and then there's a tension T acting to the left. So F minus T is equal to that. Done. If we look at this equation, the second equation, we can see that suppose that alpha is equal to 0. So all this acceleration is happening, but there's no vertical acceleration. Okay, so that means that this tension has to equal the weight of m1. So tension is equal to m1g when alpha is 0. If alpha is, say, positive, that means m1 is accelerating up relative to m. That means that the tension in that rope must be bigger than the weight mg. How much bigger? Well, by alpha times m1, the acceleration upwards. Okay? Similarly, there's another equation involving the tension that refers to this mass. So it says that the tension is simply equal to the mass times the acceleration. The only force acting to the right on m2 is the tension. So that force acting to the right is causing the acceleration a minus alpha of m2. So you just have force is equal to mass times acceleration of m2. Okay, so you could have guessed these 3 equations and written them down without any work. Or alternatively, you should do the work and then double check. Okay, that all makes sense. Okay, great. So basically this is 3 equations in 4 variables. So there's 4 variables here. There's the force, there's alpha, what else is unknown here? A, and T. So there are 4, assuming that the masses are known, there are 4 variables here. Okay, and these are 3 equations, which means that you are able to solve for one variable in terms of the other. And that's really what we're going to do. We're going to, at the end of the day, we're going to specify, for example, alpha. Okay, so that is no longer an unknown. Okay, so my battery died there at the end there, so I just wanted to make sure we got this. So in this set of three equations, there are four variables. There's the force F, there's the upward acceleration alpha, there's the acceleration A of big M and little m, one to the right, and there's the tension T in that rope. And so these are four variables, okay, and we have three equations. So what we need to do is specify one of them as specified and given. And so, a natural thing would be to say, well, let's demand that alpha equals 0. Okay? And if alpha is 0, then then there's a unique solution for these three equations and three unknowns, and then you can solve for the critical force F0. So F0 is the force when alpha is equal to 0. And so that's what we're going to do. I mean, you can solve these equations for F in general, for a general alpha, and that's a good exercise for you to do, but I really just want to focus on the case alpha equals 0. Okay, and then the equations become really easy to solve. We don't need these equations anymore because all of this stuff is encoded in here. Okay, so we're good to go. Let's make a little bit of room here. Okay, now it gets actually interesting. Physics gets involved. Okay, so great. So now we just solve these equations. So with alpha equal to 0, this is easy. Equation number 2 says that the tension T is equal to m1g. So T is equal to m1g. When alpha is equal to 0, then equation 3 says that T is also equal to m2a. M2 capital A. M2 capital A. M2 capital A. Okay, and what else? That's it. Okay, and so we have three things that are equal to each other. And then we can go back into this equation, we can solve for F. And in this case, we're talking about the critical value of the force such that alpha is equal to 0. This thing doesn't accelerate up or down. So what is that? So F0 is equal to the tension T, bringing negative 2 to the right-hand side, plus m1 times A. Okay, so we have an expression for the tension T. It's just equal to m1g. And we have an expression for A. So we go big M plus little m1 times A. What is A in terms of known things? Well, it's m1 over m2 times g. So when you're solving these equations, always try to express the answer in terms of things that you know, like all the masses and the value of g. Okay, so that's that. And I'm going to leave it okay, so this force is proportional to g. I will leave it as an exercise for you. It's one more line of algebra here. I will just write down how this simplifies. It's really quite nice. So it says that critical force for 0 alpha turns out to just equal m total. So m total is, let me write it down over here. M total is the total mass involved in the system. So that's big M plus M1 plus M2. So obviously M total. Okay, so it turns out to be M total times G times a dimensionless ratio of masses, M2 divided by M1. So you can see a force is a mass times acceleration times a dimensionless ratio of two masses, M1 over M2. If M1 is small compared to M2, the force is small. If M1 is large compared to M2, the force is large. Okay, so this is an interesting result that we're going to think a little bit about. So that's one thing, and then let's solve for the acceleration. Okay, and so the acceleration is just equal to, from this equation here, the acceleration A is equal to m1 over m2 times g. It's equal to that. We can also express the acceleration A in terms of F0. So we have an m1 over m2 times g. Well, what's that? m1 over m2 times g, just take the m total down here. It's F0 divided by m total. Okay, so we're going to solve for all of these variables, F, A, and T first, and then we're going to talk about it. Okay, so, and then the tension T, well, that's trivial. It's just M1G. We already wrote it down. Okay, so this is our answer. Okay, now comes the fun part. Now we think, does this answer make any sense? So let's see, which one should we start with? So actually, let's start with this one over here. Okay, so crucially, what we're demanding is that alpha is equal to 0. If alpha is equal to 0, m1 is not accelerating up or down relative to m, big M. And so that means that m2 is not accelerating to the right or left relative to big M. It means that all three masses are accelerating together with exactly the same acceleration to the right only, which is capital A. So you can imagine, in this case, you can just take m1 and glue it to big M, and m2 and glue it to big M. It's one just big mass accelerating to the right. And so then the answer for that special case of alpha equals 0 is simple. It says that the acceleration of the whole conglomerate is the applied force, so the external force acting, divided by the total mass. So this is correct. That one gets a check mark. Okay. The second thing to look at, the second easiest thing to look at, what was I going to do? Oh yeah, this one. So this one over here, it says that when the acceleration of m1, there's no upward or downward acceleration of m1, only horizontal, that means it must be the case that the net vertical force is equal to 0 on m1. Well, there's a weight pulling down of magnitude m1g, so that means that the tension has to equal m1g in this case, and so the forces are balanced. Okay, so this result, that gets a check mark, so that's right, that makes total sense. Okay, and then the third thing I wanted to look at was what is the acceleration of the system? Okay, so the acceleration of the system is, this is the interesting part. So the acceleration of all three masses together is equal to m1 over m2 times g. And you might wonder, actually let's put that down here. The acceleration is equal to m1 over m2 times g. Okay, now there are three special cases here to think about. So first of all, when m1 is equal to m2, when these two masses are equal, it tells you that, that for this critical value of force, it tells you that there is a particular acceleration. When m1 equals m2, we get an acceleration of g for m1 equal to m2. Okay, and so you might ask why? Why is that? So here's one typical physicist answer is to say, well, let's see, what other acceleration is there in the problem? Oh, well, there's the free fall acceleration of gravity. So what else could it be? Right? So there's a what else could it be reasoning here. Okay. However, let's do a little bit better than that, and let's say, let's take the case. I just want to sort of write this nicely. So equals g. Okay, and then let's take the case that m2 is bigger than m1. So if m2 is bigger than m1, m2 is bigger than the denominator, that means that the acceleration of the whole system together is now less than the free fall acceleration of gravity. Okay. Sorry, I just want to say this a little bit differently. So what this is saying, remember, is that we are applying some critical force to the whole system so that this thing does not accelerate down or up in the presence of a gravitational freefall acceleration g. And then, kind of curiously, it turns out that whatever that force is, well, it's this thing over here, turns out that that force will cause this thing to accelerate with all three masses together accelerate with an acceleration of g in the case that the two masses are equal. Okay, now to further understand that, we'll imagine the case that m2 is bigger than m1. Okay, so now our situation looks like this. m2 is a big mass, and it's connected, to a smaller mass like this. Okay, and then this whole thing is accelerating. Everything's accelerating with the same acceleration. Now, the point is, because there's a weight m1g acting on little m1, this tension is m1g. Okay, because this guy's not accelerating up or down, which means that this tension is m1g. Okay, and so if we make this mass large, it's under a fixed amount of tension, just m1g. Imagine this is fixed and we're adjusting this m2. Okay, so in this equation, m1 is fixed and we're adjusting m2, making it bigger than m1 or smaller than m1. If we make it bigger than m1, okay, then it's a big mass under this given force is going to have slow acceleration, okay, gentle acceleration. And because everything must accelerate with the same acceleration, then everything, including like big A, big A, is going to be less than this value, G. Okay, and then in the other extreme, we say, well, now we have a small mass. Suppose it's really small compared to the same M1G. So because this is not accelerating up or down, there's the weight down, there's the M1G pulling up, forces are balanced, no acceleration in the vertical direction. If that tension is M1G, this tension is M1G. But now we have a force M1G acting on a really small mass. Okay, and so that means that this mass has to accelerate rapidly to the right. Okay, but everything accelerates with the same acceleration, A. So that means A must be rapidly to the right, and so it must be bigger than G. Okay, so that happens in the case that M2 is less than M1. Okay, so that's really cool. So that's one thing that can be said about all of this stuff. So now you've looked at the answer. This is the answer. You've looked at it, and it makes some sense. But now comes a really cool thing. What we do is we interpret this whole thing in terms of an artificial gravitational field. Okay, so do I have enough room here? Yes, I do, I think. So we're going to take this little space here to draw a picture of big M. Put it a little bit lower. So here is big M. And here is M2 stuck on top of big M. And it's connected with this pulley over here. Like this. Okay, so that's our picture. And now the idea is we've normally, and we should normally, be viewing any kind of system with masses in motion from the point of view of an inertial frame of reference. But now what we're going to do is we're going to view it from a different frame of reference. We're going to view it from an accelerated frame of reference. Because remember, in the special case that alpha is equal to 0, okay, all of these masses they might as well just be glued together, and they might as well all be, accelerating. I mean, they're all accelerating with the same acceleration to the right, like this, okay? And so we can just take a point of view of someone standing, in this frame of reference that is accelerating to the right. So here we have the entire frame of reference is accelerating to the right with an acceleration A, and so this is a non-inertial reference frame. Okay, so from that non-inertial reference frames are perfectly valid. That's how Einstein came up with, his equivalence principle, which was an inspiration for general relativity and all that kind of stuff. So don't be afraid of looking at things in non-inertial reference frames. In fact, it deepens your understanding of the physics involved, okay? In fact, we're going to have an artificial gravitational field. From Einstein's perspective, that's exactly the same as a real gravitational field. But anyways, so what we have is a non-inertial reference frame, which means that the whole thing's accelerating because it's accelerating to the right. And so what this person would experience is an artificial gravitational field in this direction. He would say, I am in a room, okay, where if I were to drop an object, okay, I'm holding an apple in my hand and I were to drop it, well, that apple, whatever velocity it had at that instant of time I dropped it, it would keep that same velocity. But then everything else in that frame of reference would speed up and eventually take over that apple, or overtake that apple. And so from this guy's point of view, when he drops an apple, he sees it accelerate this way with an acceleration capital A. And so we say that, yes, this guy is in an artificial gravitational field. Artificial gravitational field A. Just like we're in this gravitational field G. Okay, this guy's in an artificial gravitational A, that way. Okay, he's also in this gravitational field this way. Just focus on the horizontal component of this gravitational field. Okay, so there's that. And so then he would say, you know what? If I'm in this artificial gravitational field, if I hold an apple like this and let it go, from my point of view, it accelerates that way. So I know that if I were to cut that rope, this mass, M2, and me standing on top of it would accelerate this way, okay, with an acceleration A. And so just like I say, yes, like Newton, right? He says, well, I see this thing accelerating down with an acceleration G. And so I know F equals ma. So there must be a force. F equals the mass of this object, the inertial mass of this object, times G. And I invent a gravitational force, okay? Well, it turns out that Newton's invented gravitational force is identical to this guy's invented gravitational force. They're identical. Newton's gravitational force is in the same way fictitious as this kind of gravitational force is fictitious. When you learn general relativity, you will see that. Okay, it's really cool. Anyways, blah, blah, blah. So this guy says, yep, if I were to drop this thing, it would accelerate with acceleration g. So therefore, I invent a force. I say, well, there must be a force acting. And what is that force? Well, that force that's acting, so what did I want to call it? I don't know what I want to call it. F artificial gravity. F artificial gravity force. Okay, well, what is that? Force is equal to the inertial mass of the object in question, which is mass m2, times the free fall acceleration it would have if you let it go. Okay, well, that's capital A. Okay, and so then you look, well, what's that? M2, what's capital A? We figured this out. Capital A is m1 over m2 times g. So we multiply by m1 over m2 times g, and voila, m2 cancels out, and we get m1g. So according to this guy, in this artificial horizontal gravitational field like this, he says that that artificial gravitational force is exerting a force of magnitude m1g to the left on the block I'm standing on. Oh, but wait a minute, then he looks at that string and he says, well, what's the tension in that string? Oh, it's also m1g. And so he says, yeah, that makes sense. It makes sense that this block is not accelerating relative to me because there's a force pulling that way of magnitude m1g and a force pulling that way of magnitude m1g, and the forces are balanced, and hence there's no acceleration in my accelerated non-inertial reference frame. So it's really cool. Lots of fun. Yeah. So in this problem here, basically this was a relative acceleration problem. What I want you to focus on is make sure that when you're writing down accelerations, these are accelerations relative to an inertial frame of reference. When you're drawing free body diagrams, make sure you identify all of the objects in motion, okay, and show all of the forces. And when you're done, just independently do this one, independently do this one, independently do this one, then check. For every place that they're touching, and there's an action force, there's also a reaction force. Look for all of the action-reaction pairs. Make sure you haven't missed them, okay? And then the rest is just crank out the equations and solve them, and then you come down to something like this, and then you're not done. The next step is to make sure that all of these equations make sense, okay? And then with this example, there was this added bonus that we could think about an artificial gravitational field, and I could point out that this Newtonian gravitational field is exactly as artificial as this guy's gravitational field, okay? Anyways, you'll learn that in general relativity, which is very cool. Okay, very good.